Please title these notes Graphs 3 Notes, Sketching Derivatives and Antiderivatives, and write today's date. By the end of this lesson, you should be able to translate 3 line charts and sketch derivatives and antiderivatives of functions. The integrals and derivatives of calculus allow us to draw conclusions about a function based on information about its derivative and its second derivative. This is used extensively to solve optimization problems, like what's the maximum profit a company can make, what's the maximum distance the Bay Bridge will sway during an earthquake or a windstorm, that kind of thing. This sort of analysis is super important because this is the sort of thing that happens when a bridge moves beyond its calculated maximum. This is our very own Bay Bridge in 2009. Basically, a windstorm made the bridge sway a whole bunch. It went too far beyond its calculated maximum, and a reinforcing metal chunk fell on the bridge during rush hour. Oops. Fortunately, no one was injured, but had that truck there been a little bit closer, it would have come down right on top of the person inside. Phew, very, very close call. So this stuff is really important. It's a lot of what calculus is used for in the applications. And our goal for today is to figure out how a function, its derivative, and its second derivative are related so that we can use one to figure out information about another. So for example, we can use a derivative to figure out when a function has a positive or has a maximum or a minimum value. So to do this, we're first going to look at a function derivative and second derivative that occur very nice and analyzably in nature. That's position, velocity, and acceleration. Remember, change in position over time, that's velocity, that's its derivative. Change in velocity over time, that's acceleration, that's the derivative of that, or the second derivative of the original function. We'll observe the relationship between the graphs of these as moving man moves, and then we'll talk about what these mean for f, f prime, and f double prime in general. Remember what these graphs are showing. They're just tracking, graphing moving man's position for this top blue one. As he moves, his velocity, more and more and more positive, less and less and less positive until it's 0. Right there, and then going back in the negative direction, negative velocity there, and then acceleration. Which direction is his velocity changing in? Looking at a printout of these graphs, we can use them to try to fill in this table down here. What happens with velocity when acceleration is positive? How about position when acceleration is positive? What happens with acceleration when velocity is 0? And so on and so forth. So, let's look at these and see what we can find out. Let's first just look at when acceleration is positive versus negative. So there's a switch right here, and right here. And notice that when acceleration is positive, right here and right here, velocity is increasing both times. In fact, that's the only time that velocity is increasing. So what that means for us, it means that if acceleration is positive, velocity is increasing. And notice also, position is concave up here, position is concave up right here. Those are the only times when position is concave up. Looking at when acceleration is negative, notice velocity is decreasing both times. And position is concave down both times. When the acceleration is 0, so right at these points, velocity has either a minimum or a maximum. And by definition, position is switching from concave up to concave down, and so on and so forth. So position has an inflection point. Okay, so let's switch to looking at what happens when velocity is positive. So that's this next column right here. So here are the zeros. Velocity is positive, velocity is negative, velocity is positive, velocity is negative, velocity is positive again. There we go. So going up, we can see that when velocity is positive, position is increasing. Those are the only times when position is increasing. And logically enough, when velocity is negative, position is decreasing. And this makes a lot of sense, because if velocity is positive, then the change in position is positive. Moving man should be going to the right. His position should be getting more positive. And notice when velocity is 0, relative maximum, relative minimum, relative maximum, relative minimum. Right there. Now let's look at what happens going down, though. So positive velocity, negative acceleration. Negative velocity, negative acceleration, positive acceleration. There doesn't look like there's any relationship here. When velocity changes from positive to negative, that's not telling us anything about acceleration. Okay. So let's go ahead and look then at our final row. When position is positive versus negative versus 0, what does that mean? Well, position is negative all the way up to 10, and then positive the rest of the way. So if we look on this half of the graph, velocity is positive and negative, acceleration is positive and negative. And same thing for when position is positive. So it turns out that position being positive, negative, or 0 actually tells us absolutely nothing about this left side of the graph. So positive, negatives, and zeros are filling in the right side over here. And notice there's a pattern. Positive to increasing, positive to increasing. Increasing to concave up, well, that's the only concave up, concave down we have, so we can't tell if there's going to be more of a relationship here. Now, let's add in a little bit more detail about these relative maxima and minima. Notice that for velocity, velocity has a relative minimum when acceleration changes from negative to positive, and velocity has a relative maximum when acceleration changes from positive to negative. So let's just write this down here. A maximum for velocity occurs when acceleration changes from positive to negative. And that also holds true for velocity to position. A maximum for position occurs when velocity changes from positive to negative. And similarly, a minimum for velocity occurs when acceleration changes from negative to positive. Same thing for position, which has a minimum when velocity changes from negative to positive. And then also an inflection point for position occurs when acceleration changes sign. So that's positives and negatives. Or velocity has a minimum or maximum. Now, we know that these are holding true in this one graph that we saw, but let's just check another couple examples to make sure they're always going to hold true. Now, let's look particularly when velocity is 0. That's what we're looking at right here. Here we said position has a relative minimum or maximum. However, right here, velocity is 0, but position flattens out, but it doesn't have a minimum or maximum. It flattens out a little bit and then keeps going down. So one of the key things to note here is that when velocity is 0, position may have a relative maximum or minimum, but it doesn't have to. Really, it's only if velocity changes sign. Notice that velocity is negative, then velocity is negative again. That's why we don't have a maximum or minimum here. At this 0, velocity changes from negative to positive. Lo and behold, there's a relative minimum. This also holds true if this is acceleration. Then we'd be talking about velocity, acceleration. So that 0 on that other page really ought to be changed just a little bit. We really ought to be saying for these relative maximum and minimum, may have. Down here, may have. And if we have a may have for this one, let's check this one and see if it's really true that there has to be an IP, an inflection point. Well, notice over here that acceleration is 0, but this is a flat line, or a straight line, excuse me. There is no inflection point here, so we can say the same thing when acceleration is 0, position may have an inflection point. However, only if acceleration changes sign. So coming back to here, same thing, we should really update this. May have. So now that we've looked at these relationships in the real world, it's really important to memorize a generalized table for the relationship between functions and their derivatives. And what this really is it's really a translation dictionary to translate from f to f prime and so on, just like we would translate English to Spanish or any other language. So this is just going to be a shorter version of the original table that we figured out. This is f double prime, f prime, and f. And remember, this corresponds to acceleration, velocity, and position. And now we're just going to record the relationships that we saw. We saw positive negative 0 translates into increasing decreasing and extrema. Maybe. Translates into concave up, concave down, and inflection points. Again, maybe. Now we just move over positive negative 0, increasing decreasing extrema. Maybe. And then the final moves over one level. Positive negative 0, positive negative 0, positive negative 0, extrema, extrema, increasing, decreasing, and then the concavity in the corner. This is incredibly important. This must be memorized or the dragon will come and gnaw on you. Very, 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 very important. I actually made myself a little card with it on it, just so that I would have it to refer back to as I was memorizing it. A couple of things to note. Leave yourself some room over here. We're going to add something else in here. But minima occur if the function to the left changes negative to positive. Maxima occur if the function to the left changes positive to negative. IP occurs if the function 2 to the left changes sign. Over here, I'm going to give you the expanded table. Notice that there are patterns over here, where basically just these diagonals are the same. So one of the things that we could do is we could actually just expand this table both up and to the side. So here I'm going to do f double prime. Here I'm going to do f prime. Here I'm going to do f. And here I'm going to do the integral of f. We can start with what we have over here. You should be able to fill this in quite quickly. Positive negative 0, positive negative 0, positive negative 0, inc dec ext, inc dec ext. But notice that we don't have to stop there. These diagonal patterns just continue. So what this means is it means that if we're asking about the integral or the antiderivative of f, and we know that f is an increasing function, then the antiderivative is going to be concave up. Just like we can translate with these three right here, if acceleration is positive, we know that position is concave up. If f double prime is 0, then we know that there's a possible extremum at f prime, and so on and so forth. We can also expand that even further. What you should have memorized is you should have this table over here memorized, and then you should recognize the pattern so that you can expand it into this table if and when you need to. Let's look at how we use this translation dictionary. I do encourage you to make yourself a little card with what we need to memorize on it. I find it very helpful myself. And let's look at translating f prime, and f double prime graphs. So first, let's translate some three-line charts. Translate the three-line chart for f prime of x into three-line, I put that in quotations because they're not actually going to be 3 lines, for f double prime and f. So given to you in the problem is here. This is f prime. At 2, there's an inflection point, concave up on the left, concave down on the right. At 1, there is a minimum. At 3, there is a maximum. Decreasing, increasing, decreasing. At 0, there is a 0, positive on this side, negative on that side. Now, again, remember, I'm giving this to you. There's no way that you could know that except for the fact that I've given it to you. But what we can do is we can go and we can translate this. So, let's go ahead and put f double prime over here. And all I'm going to do to translate is I'm going to get out my little chart here. And I'm going to say, okay, f prime of x. Anytime that I see that f prime of x is concave up, that translates into increasing for f double prime. So for f double prime, this concave up line translates into an increasing decreasing line. So at 2, on this side, concave up translates into increasing. On this side, concave down translates into decreasing. You can see there's a relative maximum at 2. Now we can do a similar translation. Increasing, decreasing in f prime becomes positive, negative in f double prime. Decreasing translates to negative, increasing to positive, decreasing to negative, and these are zeros. Now let's go the other way. We're going from f prime to f. Notice that we don't have a level. Here's f prime, concave up, concave down. We don't have a level there, so we're not going to put anything there. Just like here, there wasn't a translation from f prime to f double prime, so we didn't have anything right there, just like in language. Now, sometimes things don't translate. So that we can leave blank. But this one, f prime increasing, decreasing, translates into f concave up, concave down. So here's 1, here's 3. Decreasing, concave down, increasing, concave up, and these look like they are inflection points because concavity changes. Okay, for this one, positive and negative translates into increasing, decreasing. positive increasing, negative decreasing. And there we go. We've done our translations. Let's have you try this next one. I want you to translate the three-line chart for f of x into three-line charts for f double prime, f prime, and the integral of f. So you're going to use the entire table on this one. Go ahead and try it on your own, and then start the video again when you're ready. Pause the video now. Okay, so let's look at how all this works. We've got f. Let's go to the right first. So this is going to be the integral of f. Concavity doesn't translate. Increasing, decreasing translates into concave up, concave down. So we've got -1. Increasing becomes concave up, concave up. Notice there is no inflection point here. An inflection point occurs when the function changes concavity. Here it's not changing concavity. This final one, plus minus, translates into increasing, decreasing, decreasing, increasing. Going the other way, f prime. So we know that for f of x, concave up, concave down, translates into increasing, decreasing. Oh, I should have marked over here, there is a 0, or increasing, decreasing, there is a minimum here, even if there wasn't an inflection point up here. So increasing, decreasing, so this is concave down, decreasing, concave up translates to increasing. So there is a minimum. Increasing, decreasing in f translates to plus minus in f prime. Increasing is positive, positive, but there's still a 0 here. And then positive, negative in f doesn't translate. Okay, so the final one, f double prime, we can actually just go straight for doing from f prime to f double prime because we've already done the translation from f to f prime, so it's the same thing to go the next one over. Increasing, decreasing. The next one over is positive, negative. And notice that nothing else translates. So our final answer should look like this. Notice that when we say there's a 0 or a minimum or an inflection point, we need to be very specific about what level of function we're talking about. F prime of x has a minimum at the same value that f of x has an inflection point, at the same value that f double prime of x has a 0. So we can't just say there is an inflection point. We have to say which level has an inflection point. Okay, finally, let's show how we use this to do problems. So what we're going to be using this for now, we're going to be using it for a lot more later on, is going to be using three-line charts to sketch. Identify the three-line chart for f prime of x below and use it to sketch f double prime and f of x. Actually, I should say use it to sketch possible graphs, especially for f of x. There are going to be many graphs that we could sketch. We just have to do one that could be a possible graph. So let's start out with f prime of x in the middle here, and f prime of x just looks like this. It's actually an x squared function. X squared minus 4 would be this one, in fact. 0 is at -2, 0 is at 2. Let's start off by sketching its 3-line function. So on top, we're going to do concave up, concave down. It's concave up for the entire thing. Next, we've got increasing, decreasing. It's decreasing until x equals 0. And then increasing after that. So that means there is a minimum for f prime of x right there. And then plus minus, -2 and 2, positive here, negative here, positive here. Now, let's go ahead and translate that. So over here we're going to have f of x. If we get out our little card, we see that when f prime is concave, there's no translation. When f prime is increasing, f of x is concave up, concave down. So decreasing, concave down, increasing, concave up. So that means there's an inflection point right there. Positive, negative, and f prime translates into increasing, decreasing in f. So positive translates to increasing, negative to decreasing, positive to increasing. So we've got a maximum and a minimum right there. So let's go ahead and sketch this up here. We know that we're going to have a concave down piece and then a concave up piece, and that matches with this increasing, decreasing, increasing. We don't know if it's all up here or if it's all down here or wherever it is, because we don't have a positive negative graph. And yeah, there's no way for us to know it, so just sketch it wherever. But we should definitely have at -2, at 2, and at 0 some special things going on. So we should have increasing until -2, then a maximum, then decreasing, then we should have an inflection point at 0. So now we've got a cup shape, continuing to decrease until 2, and then up again. Something like that. Then we can also do our translation going the other way, f prime to f double prime. Concave up, concave down translates to increasing, decreasing. So it is always increasing. Increasing, decreasing translates to positive and negative. So 0, decreasing is negative, increasing is positive. So that means for f prime of x, we've got some function that's always going up. It's going to be negative on this side of 0, positive on that side of 0. We don't know if it looks like this, like an x cubed, or straight, like a linear function. Generally, as we take the derivative, our function gets flatter and flatter and flatter. So our best guess is probably just a line like that. And if we do our work with our actual derivatives that we know how to do, we can actually confirm this. This I happen to know because I wrote it. Is this function. You can tell though that it's some sort of x squared minus something. And that means that when we take the derivative of x squared is 2x, and whatever this is, it doesn't matter, it's going to be 0. So that means this is 2x, it is indeed a linear function, just like we drew it. And over here, if we take the antiderivative of f prime, that gives us f of x. So we add 1 to the exponent, divide by the new exponent. Antiderivative of -4 is -4x. And yes, we have some sort of x cubed sort of little function. Now the key thing here is that this plus c, this is why this plus c is so important. Because the plus c tells us that we have no idea what the positive negative line is. This could be moved up and it'd be correct, it could be moved down and it'd be correct. That's totally fine. Okay, one final check for understanding problem, and then we're going to be all done. There's one little trick to this. So you might have one question on how to handle one particular thing, but do all that you can and then come back and look at the video. Identify the three-line chart for f prime of x below and use it to sketch possible f double prime of x and f of x graphs. So here's f prime of x. It looks like that. Okay, go to it. Come back when you're ready. Okay, so here's the thing that's tricky about it. Concave up, concave down? It isn't. It's just some straight lines. We can still do the rest of them like we normally would, though. Increasing up to 0, decreasing after that. Oh, so there is a maximum right there. Always negative on that side, negative on that side as well. So let's translate to f of x. No translation. Translates to concavity. So increasing to concave up, decreasing to concave down. There's an inflection point right there. Positive negative translates into increasing, decreasing. It's always negative, so that means decreasing, decreasing. We'll go to sketch it. So we've got something that we've got a cup-shaped piece and we've got a dome-shaped piece. But it's always going down, so we can't do our sort of sinuous function like we did before. We've got to sort of chop it off. Concave down, and before it starts going back up again, that's where we switch. We've got to do the downward side of the dome because we're only allowed to go down. Just like basically if I do it with my hands, here, this cup shape, we can only use kind of this original part. We can't use the part where it's going back up again. Whereas with the dome shape, we can only use, again, this part. We can't use the part that would be going up. So that means, again, we have no idea if this is above or below the x-axis. It really doesn't matter. We're just going to be doing that cup shape up until 0, and then the dome shape after that. Looks something like that. This could be above, wherever. Now let's translate the other way. F double prime of x. So concavity translates into increasing, decreasing. And let's see. This says none. So if we think about what that means, it means there's no increasing and no decreasing. Well, how can that be possible? How can we have something that's neither increasing nor decreasing? Well, the only option is for it to be a flat line. If it's a constant function, then it's okay. Increasing, decreasing translates into positive and negative. Let's see, did I write? Inflection point, yes, there's no maximum or minimum here. So over here, we've got decreasing translating to, or increasing, excuse me, translating to positive, decreasing translating to negative, and let's see what we can do here. This is a tricky one to figure out. So if it's a flat line, that means on this side of 0, it's a positive flat line, so somewhere up here. And on this side of 0, it's a negative flat line. Something like down there. And what happens at 0? Well, somehow it has to get from positive to negative without being tilted at all. So what that means, the only way that we can do that, it seems really weird to do, is that we basically got this little break here. This over here is a positive flat line, and then at 0 it jumps down to being a negative flat line. And at 0 itself, there is no second derivative. And if we stop and think about it, that actually makes sense, because we know that when we have a sharp turn, a function is not differentiable. We can't take the derivative at this point. So that means that for f double prime, there shouldn't be a value, because there isn't a derivative of f prime. Also, this makes sense. This is a constant positive slope, constant positive value. Constant negative slope, constant negative value. That concludes these notes.